Okay, so we have 3 minutes. Okay, so I'm Sim. Okay. Yeah. Let me just begin a run through on yeah, now it's our RMO, so it's our book B, right? So I believe all of our students just clicked our book B last week. And then this week we are going to run through the first 10 questions, which is about calculation. So in RMO, calculation is a very important part. But yeah, in APMOPS is SMOPS, they really ask difficult question about the calculation. But yeah, SMOPS mainly focus on maybe counting and combinatoric. Yeah, but RMO, there are always 3 or 4 questions in the first round, and it's really difficult. Which means yeah, we should reach a high level of the calculation questions. Yeah, I got a COVID positive, so my throat is, yeah, you know. So maybe I can only speak in this voice today. So sorry for that. Okay, now the first I see 1, 2, 3. Yeah, the first 1, 2, 3, the first 3 questions, they are all about a certain point, which is what we call the fraction, splitting, aka fraction decomposition. Which means that we want to write a fraction into the sum or difference of other two fractions, and then use this to cancel many terms between them. So the basic logic for this, so how can we do the fraction decomposition, is that if the denominator is the product of several numbers, and the numerator is the sum, or more often difference of this number, or the numerator is a constant number, which means we can turn this constant number into something we needed by multiplication or division. So this is the basic case. But as we can see, so we already run through the basic fraction decomposition in our book A. So in book B, I just put 3 questions, which is not that typical. We need some advanced technology to turn it into a normal form of decomposition we know. So for example, the question 1, so we will see that, so if we look at only the denominator, it's a very classic decomposition one, because it's the multiplication, the product of 3 consecutive numbers. So if it looks like this, if this looks like this, then we know how to solve it, because we can use the decomposition one to calculate it easily. But the problem is, so now the case is that the denominator is suitable, but the numerator, they are not a constant number, right? They 3, 5, 7, 37. These are not, which means we should do the transform from the numerator first. And then maybe we can observe. So what's the relationship between the numerator and the denominator? So the numerator is an arithmetic sequence. The common difference will be 2, which means now this is 3. This is 3 plus 2. Now this is, so 7, right? We can write 7 into maybe 3 plus 4. Or 37, we can write it into a 3 plus 34, right? So if we write it into, the first term and plus the common difference, and 17 of common difference. If we write it this way, we can express all the numerators in a different way, but still, we cannot see the relationship between the numerator and denominator. But luckily, we can use the same way. So in this way, we keep a 3 here as the first term, right? What if we remove another common difference, another 2 from the 3, which means, we turn the 3 into 1 plus 2. So we use 1 as the initial number, and 3 is 1 plus 1 common difference, and 5 is 1 plus 2 common difference. 7 is 1 plus 3 of the common difference. And then in the end, the 37 is 1 plus 18 times of the common difference. So the numerator does not change. I just change the expression. But now, interesting happened, because here, if the 2 times 1, 1, 2, 2, 3, 3, 18, 18. See what's the difference. Because now we have the number in the numerator and the denominator, they are both the same, which means we can do the cancel thing. And then the logic's simple. So firstly, we just split each fraction into 2. So into 1 over 1 to 3 and 2 times 1 over 1 to 3. And so 1 over 234 and 2 times 2 over 234. The third one, 1 over 345, 2 times 3 over 345. Now in the end, lastly, it will make into 1 over 18, 19, 20, and 2 times 18, 18, 19, 20. And we can cancel the 1 here, 2 here, 3 here, 18 here. So now the equation are split into two parts. So one part is that the 1 over 1, 2, 3, 2, 3, 4 till the 18, 19, 20. The second part, after we cancel the 1, 2, 3 here, is the 2 over 2 times 3, 2 over 3 times 4, until the end will be 2 over 19, 20. And both of this part can use the splitting term to easily calculate it. So the first part, right? So the difference of the last and the first is 2. So it's, and the first term, 1 over 1 plus 2, 1 times 2. The last term, 19, 20. Then plus, now here, we have this 2 out because the difference is 1. And then this is 1 over 2, 3, 1 over 3, 4. In the end, it's 1 over 19, 20. So make it to be 1 over 2 minus 1 over 20. Now then, end of story, we can just calculate it out. So this is, which will make it into, yeah, not that easy to calculate. It's 189. Yeah. So this is 760,189 plus. Now here is 1 minus, so this is 9 over 10. Now this is a 9 over 10. So which means, so 9 over 10. 9, 4, 9, then minus 79, so 76. So this would be 8, 7, 3, 7, 6, 0. Yeah, then this would be the answer. So now for this question, so the key point is to get the numerator into a familiar form. So in this case, maybe 1 plus 2. So this is the arithmetic sequence, which means we can turn this into a constant number 1 plus the common difference times the number of terms. Yeah, this is a very common way of transforming because, yeah, for arithmetic sequence, it can always be written as the number of terms times the common difference plus a constant number. So this constant number, we always call it the zeroth term instead of the first term, because first term is the zeroth term plus the 1 times common difference. So the zeroth term, yeah, not that common in primary school. Yeah, but it's very common in secondary school. Okay, so this is the first question. And for the second question, so now this is not that easy to calculate because if you just look from the front to the end, it's not that easy to find a pattern. But if you look backward, so look at this one. So for this fraction, it's easy to find that there are many things to cancel. So it can be simplified. So how many numbers are to be simplified? So the numerator is 100 to 4. Denominator 97 to 1. Yeah, maybe we can just Yeah, from here we can see the 199, 98. And then is 97 to 4. And here is 97 to 4 times 3 to 1. So it's quite easy to find that the 97 to 4 can be cancelled, which means now this number can be written as, so the remaining is 3 to 1 and 199, 98, correct? And then, yeah, maybe we trace back for the, so this is what, the 96th term, right? The 96th term. So the 96th term, it should be, so the numerator is 100 to 3. And then this is 97 to 2. Also, if we do the canceling, so this one, 100 to 5. So we write this into 199, 98, then 97 to 5. And for the denominator, it's 97 to 5, and then 4, 3, 2. So again, the 97 to 5 can be cancelled, which means the 96th term is 199, 98, and then this is 4, 3, 2. So find the pattern here. The last term and the second last term, yeah, they follow some same pattern. So the numerator is always 199, 98. The denominator, 1, 2, 3, 2, 3, 4. And then this pattern follows till what? Yeah, till this one we are very familiar with. So it's just itself, 199, 98, 97, 96, 95, right? So you can check maybe the 199, the fourth term. Yeah, you see the pattern always follow from the end to nearly the top. So now we find the pattern for nearly all of the terms. But the problem is, what about the first two terms? There is nothing to be cancelled. So there is only 2 terms and 1 terms in the numerator and denominator. So if there is nothing to cancel, can we transform it in the same way? Of course, it is. So in this case, we want to try to add something onto the numerator and the denominator. Now for this one, what if I times an additional 98 to both the numerator and the denominator? Now we still, right? So it's just the reversed version of the simplification. So in this case, the value of the fraction still not changed, right? So actually, the second term can be turned into a same form as the last ones. And the first, yeah, I believe you know how to do this. We just adding a 99 and a 98, which makes here to be 99, 98, 97. So now, using the simplification, pattern finding, and then we transform the equation into something we are more familiar with, because now the numerator is a constant number and the denominator is the production of 3 constant numbers. So maybe I reverse the order for it easier to calculate. Now, yeah, it's very easy to calculate those inside the bracket. So the difference, 3 minus 1 is 2. So 2 over 1. The first term, 1 times 2. The last term is 98 times 99. So notice that in this case, so we don't do the unify the denominator here. So we just use the distribution law, right? It will be quite easier. So if we use the distribution law, so this is 1 over 2 and 1 over 2. So which can be here, then minus. So now here, just minus 15 because we cancel 99 and 98 and cancel a 2 here. So now for this one, this is 20, so 49, 15, 49. So this is 2428, 2550. The minus 15 is 242500. Yeah, this is an integer answer and quite a large integer, I have to say. So now this is the second question of the fraction splitting terms. And the third question is a little bit different because instead of splitting into difference, this question is about splitting fractions into their sums. I will see from that. So now this, we have two parts. The first part, we will see 1 over 1 times 2022, 2 times 2021, and then till the end. So maybe just look at this. For each fraction, we will see the numerator is a constant number, denominator is the product of two numbers. But the difference of these two numbers are not the same. Instead, the sum of the two numbers in the denominator is the same. So if we want to do the splitting term, we can either turn into the sum or the difference. It depends on whether the difference or the sum on the denominator is the same. So in this case, so which is the same? The sum is the same, right? So we can turn the numerator into their sum. The sum, which is 2023, so I make it into a 2023, 2023, and then 2023. So as long as the denominator is the product, and we can use the splitting term. And in this case, if in the denominator the sum is constant, then we change the numerator into sum. The difference is constant, we change the numerator into the difference. So it just depends on how the denominator looks like. However, if the original numerator is 1, so we should times additional 1 over 2023. So this is the first bracket. And for the second bracket, it's more likely because we see the sum of these numbers are what? A 2022. So we have a 2022 outside the bracket. So we just times the 2022 inside will be okay. So we left only the 2023 outside, and then inside is just 2022, 2020, 2022, and then till the end. So it's 2021, 2022. So this is the preparation step. And after that, we can easily do the decomposition. So each of this number can be the addition of two numbers, right? So this one is 1 plus 1 over 2022. The second one is 1 over 2 plus 1 over 2021. And the last one is 1 over 2022 plus 1. Which means we just add 1 over 2 and till the 1 over 2022 each twice, right? And for the second part, it's the same. But the first is 1 plus 1 over 2021, 1 over 2 plus 1 over 2020, till the end, 1 over 2021 plus 1. Of course, we cannot calculate it, but this is a subtraction, not addition. There are so many things in common in both the first bracket and the second bracket, and luckily, they all times and 1 over 2023. So we can cancel everything we want. So this is 1, 2, 2021. And then we have 1, 2 till 2021. So we can cancel all the 1 over 102 and 1 over 2021. And then what's the remaining will just only be 2 of 1 over 2022 inside the bracket. And don't forget to times an additional 2023 here. And so the answer would be, yeah, maybe in the end we need to calculate this out. Luckily, it's easy to calculate. This is 2045,253. Now, this is the answer. Okay. Now, this is the first 3 questions, all about fraction splitting is very important. So this 3 question, maybe I think it's more difficult than the normal RMO question. Yeah, but if this year the RMO want to ask some question a bit beyond the past year's level, so I think they can reach the difficulty of this 3. So it's reasonable. So in this 3 question, it's very important for us to know how to transform a fraction into a decomposition format. Okay. And then let's move on. Okay, now this is the question 4. Yeah, question 4 is about the continued fraction. But instead of just calculating a continued fraction, yeah, this is about an infinite continued fraction. So you will see that, so this means there are infinite levels. The problem is, so how do we solve the infinite level problems? Actually, RMO have questions asking about the infinite levels. You will see after that. So they're about geometric sequence. Yeah, but yeah, in the continued fraction, there is also such type of questions. So how to solve this type? So if we want to solve an infinite questions, there is something we should remember. So first thing is that, and the most important thing. So if we add an additional 1 into an infinity, the value is still infinity, right? Because I'm already infinity. So if we're adding a 1 to me, it does not change. So infinity plus 1 is infinity. Also, infinity minus 1 is also infinity. Yeah, this is very important for the infinity calculation. So for the infinity continued fraction, how do we apply this for us to use? So now let's see this continued fraction. What's the pattern of it? So we will see from that. So maybe I write, sorry, not here. So maybe I write something from here. So we will see that we can call this, oh no, sorry, to fulfill the pattern just here. Because, right, so the denominator is 1, 2, 1, 2 in the pattern, and the integer part is 2, 1, 2, 1. So maybe I just put 2 layers together. So you will see that, so each of the adjacent 2 layers follows a pattern. So if I want to create a larger number, I just, for each fraction here, so I just adding fraction bar, divide 1, plus 2, then over a new 2, then plus a new 1, right? So now this will make a new fraction adding a new pattern, right? Adding 2 more layers and 1 new patterns. So this is how we build this continued fraction. So following this pattern, we know how to build it. And then if there are already infinite layers here, so maybe we assume, right? So we assume this infinite layer, so this fraction equal to x. So this one equal to x. So x is the value of the whole fraction. And then x is what? Is the infinite layer. Now let's try something. What if we add 2 new layers or adding 1 new patterns to this x? So how do we adding a new patterns? So for x, right? So let's see before. So imagine now this is our x. So if we want to create a new one, yeah, we just adding a 1 plus a 2 over a 2 plus a 1. So now we can easily adding a new layer to x. So now making it a infinity plus 1 layers continuous fraction, right? But what do we know? So we know that infinity plus 1 is also what? It's also infinity, which means for this and this and this, they actually have the same layer. And if these two fractions have the same layer, they would have the same value. Which means the left and right, they should be equal. Because they are all, so this is still also the infinite layer of the original fraction, so it's also have the value of x. So this is the characteristic of infinity, which means if we adding a new pattern or remove a pattern from it, the value does not change. So now we build an equation about this x, because we adding 1 new layer to this x. The value is also still the x. And then we can solve this equation to get a certain value of x. And it's quite easy because we just times a 2 here. So we will get a 2x would equal to 2 plus 2 plus x. And then x is obviously 4. So the original fraction has a value of 4, and 4 should be the answer. This is something about infinity. Okay? And yeah, I believe in the book A, we have run through enough questions about the basic continuous fraction. So in book B, there is something more important, such as the infinity in the continuous fractions. Then the question 5, right? So the question 5 is something, yeah, this is a real question from the RMO. I believe it's 2015 or, or 2017 questions. So we will let me calculate the sum of all these fractions. So look at the numerators. The numerator is always 1, and the denominators, yeah, it's something strange from what we know, right? So it is 5 power of 5 plus 1, 5 power of 5 plus 5, 5 power of 5 plus 2 power of 5. So we can easily find the pattern of the denominator, but how do we solve this? So now, yeah, to solve this part of question, maybe we can try an easier way. So firstly, we can see there are many 5s, right? So there are many 5s on the denominator. Yeah, many 5s on the denominator. So maybe we just extract the 5 here, the common factor here, out to see what will happen. So now this is 5 times 4 power 5 plus 1. And then this is now 3 plus 1. And we just write it. And the fourth, yeah, sorry. The fifth Yeah, it's easy to follow the pattern. Maybe we just write this down. So these are the first 5. And then, so the middle, right, is 5 over 5, 5 to the power 5, 5 to the power 5, right? So maybe we just write it into, yeah. So now this is the first half. And the second half, so maybe starting from, yeah, starting from this. So now we can extract the 5 power 5 out. So it's, now we reverse it, right? This is the 6th form. And the 7th form, so it would be, we extract the 5 power 5 out. It's 1 plus this. And then it's easy to find. Yeah. So first we turn the form into this way. So we just extract all the 5s, all the common factors out. And then we will see that we will find something in common here. So 1 plus 5, 1 plus 5. 1 plus 5 square, 1 plus 5 square. So for the first half and second half, we can always find something in common. And then for those in common, maybe we can put in them together, right? So we may need to try to pairing them together to see what will happen. So now, firstly, we pair these two together, which will make it into yeah. And secondly, so we pairing the blue ones. This is 5. And in the end, so this is the yellow one. Don't forget, right? So we have something here. So which is, so now let's try to calculate something into the inside this bracket. So we just unify the denominator, yeah, into, because 5 power of 5 is larger, so it's 5 power over 5. And then, so this is unchanged. This will times additional 5. See, now we can cancel this 5 plus 1 and 5 plus 1 here, which means the value of the first bracket is just 1 over 5 power of 5. What about the second bracket? Still, we unify the denominator into the 5 power of 5. 1 plus 2 power of 5. And now, after the unifying, the first, the second, also, we can cancel. Which means the value of the second bracket is also 5 power of 5. Which means, yeah, we can just find out. So for the value inside each of this 1, 2, 3, 4, 5 bracket, the value is always this 5 power of 5. And then don't forget, we have an, yeah, if you don't believe, maybe try the last one, right? The last one is the 5 power of 5 times plus this. And so the first fraction is the numerator, the second numerator, right? It's the same. It's the same. And we just keep, right? The last one, we just make it into 1 over 2 times 5 power of 5. And then, yeah, so maybe we just use this. This is 5 power of 5. So this is 2 times 5 of pi. So, and this is 10 plus 1. So this is 11. So can we just calculate this out? Yeah, I believe so, because 4 power of 5 is 625 times additional 5 is 3125. And then times additional 2. So this is and 2. So it's 11 over 6250. And that is the answer. So for this question, so it's easy for me to just tell you, hey, you just pairing these two up. And pairing these two up. And then you will find that the sum of each pair is the same. Yeah, it's this 1 over 5 power of 5. Yeah, it sounds easier, right? But why didn't do that? Because the key point is, if you don't know how to do that, you didn't see this question before, how do we solve this out? Right, so this is the key point. So that's why I list all the numbers out. Just want to tell you that you can find the pattern yourself, right? So after you extract the common factors out, you will find the common things. You will find the relationship between the first and last, the second and second last, right? So the pattern is to be found, not to be told. I believe in this time, so it's not important for us to remember questions. You remember the conclusion, remember how to do it, but to try to know how to solve, how to think of this. So how to try and know and find a pattern and then find a way. Okay, now this is question 5. Question 6, yeah, still RMO real question. So now for this one, you will see that, so the sum of several fractions, so the numerator is a Fibonacci sequence. Denominator, yeah, is a very classic geometric sequence, right? So it's something like a geometry sequence, but not exactly the same, because the denominator is, but the numerator is not. But anyway, so remember when we run through the first, RMO Book A, right? So I told you, for any question involving the geometric sequence, it's always useful for we to use the multiplication and difference logic, which means, right? So for the original sequence here, we can see the common ratio is the 7, or aka 1 over 7. So we always we list up the original sequence. So yeah, this is infinite, as I mentioned before. Yeah, maybe just here and leave it behind, or maybe let's keep it. Then, yeah, we just use the whole sequence times the common ratio, which is 1 over 7. So only the denominator follows the geometric sequence. We just look at the denominator. It's 1 over 7, right? So we just times 1 over 7. So if we times additional 1, which means, so each term will move to the second term's position. So 1 over 7 become 1 over 7 squared. 1 over 7 squared become 1 over 7 cubed. And 2 over 7 cubed becoming 2 over 4 power of 7. And then 3 over 5 power of 7. 5 over 6 power of 7. 8 over 7 power of 7. Right? So this is multiplication. And then we find the difference. The difference is that we use the original one minus the multiplied one. So for the left is 1s minus 1 over 7s, so it's 6 over 7s. To the right, so yeah, let's see. So there is 1 over 7 here, right? 1 over 7 here, and a 0 here. And now here for each term, so this is 1 over 3 power of 7, 1 over 4 power of 7, 2 over 5 power of 7, 3 over 6 power of 7, 5 over 7 power of 7. So see something interesting. So now so if this is a basic geometric progression, by multiplication and difference, we can just get the value of x immediately, so we get the answer. But this, no. So still, the difference is also an infinity sequence here, right? But look at this infinity sequence, you'll find something similar with the original one. So now, the numerator 1, 1, 2, 3, 5 is still the same, right? So numerator is still the Fibonacci sequence because it's the difference between two adjacent forms of Fibonacci sequence, and following the rule, so it must be a Fibonacci sequence. It means for this infinity, so the numerator is also Fibonacci sequence, but about the denominator, so compare term by term. 7, 3 power of 7, 2 power of 7, 4 power of 7, 3 power of 7, 5 power of 7. So we will see from that, so the denominator at each term is times 2 additional 7s here, comparing with the original sequence. And then we know how to do this. Because, thank you God, so this is an infinity, right? So this is an infinity sequence, which means the infinity, although we lack of 2 terms initial, but still, infinity plus 2 minus 2 is also infinity. So which means the original infinity sequence and this sequence, they are all have infinite terms, and each term comparing with each other times additional 49 onto the denominator, which means this one would equal to what? So equal to 1 over 49 of the original sequence. And then we will get, so this sequence have a certain, is the 1 over 49 of the original. So the value of it is 1 over 49 times s. And then we would get an equation for s, because now we know that this difference here, so 6 over 7s, just equal to 1 over 7 plus this 1 over 49x. Then we may just, right? So we may just solve this s out. And this is what? So 49, 62, 61. S equal to 1 over 7. Then we get the s equal to 7 over 41. Now, the answer for this. This is not an easy question. I don't want to tell you this is an easy question, but it's very important for you that as long as you notice this is something related to a geometric progression, geometric sequence, it's always useful for us to use the multiplication and difference logic. Now, this is quite important. Okay? Then move to the question 7. The question 7, however, is not that easy to solve, actually. So because it may not be solved in a normal way. So in this case, I suggest you to find the pattern for this question. So sometimes when we face very difficult questions, so there are very large numbers, we cannot solve it. Maybe we try to solve it with, so what if the number is smaller? What if the number is with fewer, quite fewer, I mean. So if we use, right? So we, in a calculation, in the calculation, I emphasize. So if we use the annual number 2023, 2024 to make a question, so this normally means that the number can be random. So now this start with 2023. So it can also be started with 2022 or 2021 or 2024 or 1993, 1992, 1965. Yeah, it can be any numbers. So this is the annual number. So if this is the annual number, this can be any random number. So maybe we try some smaller number. How small? What if we try 2? So what if we don't start from 2023? What if we just start from 2 and go to 1? What's the pattern of this equation? We'll see from that. So firstly, maybe we just 1 over 2 and a square. And then we add a smaller reciprocal. And if this is a 2, then the smaller one is just the 1, right? So this is the first part, right? For the first part, we just starting from 1 over n. And then each time we adding 1 additional reciprocal and square. And then until we add into the 1. So this first. And the second part is easy. So we just starting from n to 1, we adding the reciprocal of them 1 by 1. So this, if we start from 2, then it looks like this. And if we try to calculate this, so the value would be, so this is 1 over 4. This is 9 over 4. This is 3 over 2. And then, so the value is a 4. And then what about 3? So for 3, it's 1 over 3. Then adding additional 2. Then adding a 1. Right? So, I know this is complicated to calculate, but I give you the answer. It's a 6. No? Just a guess. So what if I start with 2023? So if 2 is 4, 6 is 3 is 6. Guess the answer. I believe it's easy for you to have the guess. So it's just 2 times 2023. It's 4046. And then this is just the answer. Don't be surprised. So this is a pattern in mathematics. So now this tells us something. If we want to solve a problem, we just start from the easiest point. We start from here. And we find the pattern one by one, step by step, to get what we need. But, right, so now the RMO is the MCQ. The APMOPS round 1 is all short answer, which means you just guess the answer, you just write it down, then end of story. But what if we need to write process, right? Or what if I need to prove if this is exactly 4046, so Sn equal to 2 times of n, how to prove this? So actually we can prove this, but I spend a lot of time and it's a little bit complicated. So I write it down here, but I don't expect all of you to understand the logic. So for this question, you just need to know. So for a complex question, try to start with the easiest number to try to find a pattern and guess the answer out. The proof, look at this. So I just prove, instead of proof at each one, so I just want to find the difference of 2 adjacent sum. So if we start with the n, the equation looks here. What if we start with n plus 1? So if we add in an additional here, the first term, the second term, the third term, I will make a slight adjustment. And the last term of square and then, right? Yeah, let us find the difference of two adjacent sums. Now, this is something just out more. Yeah. And then between each of between each of this form. So it would be a difference of two squares, right? So you find a difference. That is a difference of squares. And the difference square equal to the sum times the difference. And the difference is always 1 over n plus 1. So then we just find the sum. So now in the first bracket, the sum is 2 of 1 over n and 1 of 1 over n plus 1. So the second bracket, the sum of two bracket is 1 over n plus 2, 2 over n, 2 over n minus 1. And then, yeah, in the end, the last bracket, right, the difference is always this 1 over n plus 1. The sum of these two brackets is 1 over n plus 1, 2 over n, and then in the end, so 2 over 2, 2 over 1. And the last bracket, right, the last bracket is just n 1 over n minus 1. The difference of this, yeah, is 1 over n minus 1. N plus 1, sorry. Right. And then, so now here, actually this one, we also have 1 and 1 over n plus 1. And here, so we have n times a 1, right? So we can write it times a 1 here. So actually, we can use this 1 over n plus 1 to cover all. But by then, what do we get? So just adding a new thing here? No. Let's see what's inside this bracket. So inside this bracket, we will see there are several numbers. And if we do a fraction addition, we want just putting those with the same denominator together because we don't need to unify the denominator, right? So let's see. So how many fractions are there with denominator n? Actually, each of this bracket contain n, right? So totally there are n bracket, so which means this 2 over n occurs for n times, which means the sum of all fractions with denominator n is 2 over n occurring n times. What about this n minus 1? So the first bracket, no. Starting from the second bracket till the end, right? So the n minus 1 occurs for n minus 1 times. So this occurs for n minus 1 times until the end. So this 2 over 2 occurs for 2 times the last two bracket. And this 2 over 1 occurs for only 1 time in the last bracket, right? And for this n plus 1, 1 over n plus 1, it exists in each of this bracket, right? So each of this n plus 1 bracket, so it's, right? Then adding additional 1 here. Then we will see inside the bracket, they're all 2, 2, 2, 2, 1, 1. So it's 2n plus 1 plus 1. Then this 2n plus 2 cancel n plus 1, it's a 2. So by finding the difference of two adjacent, we will see that the difference between two adjacent sums is always 2. So starting from 2, the sum of 2 is 4, the sum of 3 is 6, then sum of 4 is 6 times 6 plus 2 is 8. So the sum of 5 is 10. Then following this pattern, we can prove that the sum to the 2023 is 2 times 2023. It's not that easy to prove. It's not even that easy to understand. But yeah, I will show you. So to make this question, yeah, here. Okay. And then the last 3 questions. So question 8. So question 8 is about the defining operation, but it is a slightly complicated one. So now this gives us a law of new operation. And we know the m omega, this is called omega. So m omega 4 equal to 30. We're going to find the m omega 8. So there are many ways to solve this. So we can solve the m first, or we can find the actual pattern of this omega calculation. So what does this omega actually mean? We can always get the general term of this a omega b. Yeah, but yeah, for this question, maybe it's not that difficult. So don't ask a very difficult question. So maybe we just use the easiest way to solve this. So we will see that. So for an a omega n can be calculated by the so the a omega n can be calculated by the just omega n minus 1, which means we can use the m omega 4 to get m omega 5, m omega 6, m omega 7, and omega 8. Also, we can use the m omega 4 trace back for the m omega 3, m omega 2, m omega 1, right? Yeah. So the basic logic is that first we get the value of m. So the m omega 4, so we know that m omega 1 is m. What about the m omega 2? Then m omega 2, following this rule, is 2 times m omega 1 plus an m. So this is an m, so this is 3m. And m omega 3 is 2 times m omega 2 plus an m. So this is 3, 6, 7m. Then the m omega 4 is 2 times m omega 7 plus m. Sorry, m omega 3 plus m. So this is 7m. 2 times 7m, 14, and 15m. Right, 15m. So now we get what? So this equal to 30. We'll get m equal to 2. Yeah, but we don't need the m equal to 2 now because we still need to use m omega 4 to get m omega 5, 6, 7, and 8. So maybe I write it shortly because this is 2 of 15m plus 1m. So this is 31m. M omega 6 is 2 of 31 plus 1. So this is 63m. M omega 7 is 2 of, yeah, maybe I write it more clearer. So this is 2 times, and write it here. Right. So that's easier for you to understand. And for 6 and 7, maybe just here. So 6 is the same. And 7 is 2 of 63, then plus 1. So 1, 2, 7, m. Then m omega 8 is 2 times 1, 2, 7 plus 1m, which is a 255m. And we know the m equal to 2, right? So now we know m equal to 2. And then we just trace it back. So this is 5, 1, 2. No, that's the answer. But this is the easiest way. We just calculate it. But actually, so we can find the general term here. And it's easy to prove that. So m omega n actually equal to m power of 2 minus 1 times n. Yeah. But how to prove this? So maybe I skip it. It's something that the advanced use of a geometric sequence, I believe. Okay, yeah, so I just leave it here. You can find a pattern anyway. Okay. Now, question 9 is difficult. So this is something that, so the method to solve this problem is something that very likely for the sum of factor principle. So what's the sum of factor principle? So it's that, so when we want to calculate the, for example, the sum of factor of 102, right? Because one maybe easier, maybe 30, right? Because 30 equal to 2 times 3 times 5. So the sum of factor of 30 can be calculated with, so for each prime factor, it can either be used or not used when forming its factor. So the two choice is 1 plus 2. So if 2, right? If we don't use 2, then we use 1 to replace it. So if we use the 2, it's a 2. And for the prime factor 3, also two choices. What not use and use. For 5, not use and use. And so for each prime factor, we have two choices. And after we adding them together, right? For each of this choice, we adding them together and we times them together. So this is the sum of factor of 30. So I believe all of you know the sum of factor principle. And so for this one, it's just the same logic as the sum of factor principle. So in this case, so we have 1, 2, 3, 4, 5, 6, 7, 8, right? So now, it's stressed that if a product can be obtained multiple times, it will be added multiple times, which means this 12 can be added 2 or maybe more than 2 times, right? So now we have 1, 2, 3, 4, 5, 6, 7, 8. So we have these 8 numbers, and we have several products using numbers among them. So then we may treat this 8 number as 8 factors. And when we want to form a product, right? If we want to form a product, we can either use or not use one of a certain factor, right? For example, we can use 8 or we cannot use this 8. So it's all okay. But in this case, this 8, we have two choices. So use or not. So then again, if we use this 8, we just write this 8. If we don't use this 8, we use a 1 to replace it. So for the factor 8, we have two choices. And for the factor 7, two choices. Factor 6, two choices. Factor 2, also two choices. Use or not use. So for 1, it's very special because we use 1, we times a 1. If we don't use 1, we still times a 1 because times 1 means times nothing. So for 1, right, it's either used or not used. It's the same. It's the same, right? It's the same. And so we can treat this 1 to 8 as the 8 prime factor here, but the prime factor 2, 3, and 5 here, right? So for each factor, we can either use it or not use it. And the sum of all product, sum of all factors, so it's we add 1 and the factor together, and then we find the production. So this is sum of all product. However, this is not exactly the answer because when we use this way, we will calculate something we don't need. So when we find the sum of factors, the sum of factor will include the factor 1, right? But the factor 1 means we choose no prime factor among either 2, 3, or 5. Now, in this case, if each factor we can choose not, so now this is what? This is the factorial of 9, right? This is factorial of 9. And then for each number here, So for each product here, we can also choose either to use or not one certain factor. So does this contain the situation that we use no number? Of course, right? But if we contain no number, there is no product. So if no factor is used, the product is just a 1. So we should use this to minus the 1. So this 1 meaning use 0 number. So if 0 factors to be accurate. So if none of these factors are used, the product is just a simple 1. No number is type, right? But also, we should remove another because this is only use 0 factor. So is there a case that we only use 1 factor? Of course. But 1 factor still is not a product. So if we only choose 1, for example, 1, 2, if we only use 2, we don't use other factors, then the product is just 2 itself, right? So for those only use 1 factors, it will be the value is just the factor we used. So there's 1, 2, 3, 4, 5, 6, 7, 8. Right? So now this is those who only use 1 factor. So all the product minus the product use 0 factor and product use 1 factors. So this is the actual sum of factor we need. And then this is the answer. So we know the factorial of 9 is, this is number we should recall. 6362880, right? And then we minus a 1 minus, and so this is 36 or 37. So the answer is 362843. This is not easy. So this question is not easy. So anyway, you can use the finding the pattern logic. So you can try to find a pattern starting from, so because it's 1 to 8, you can start from 1 to 2, 1 to 3, and 1 to 4. But this pattern is not that easy to find because, so you will see that pattern looks like, so following this, the pattern would be, so if 1 to m, sum of product is m plus 1's factorial minus 1 minus 1 to n. So this is the pattern. And it's difficult for you to find a pattern in this form, right? Okay. Okay, now this is for question 9. And then we move to question 10. So the question 10 is that if we write several consecutive natural numbers starting with 1, so it's 1, 2, 3 till the end. And then we erase one of the numbers. So the original is 1, 2, 3 till the end. And we erased one of the remaining number. And then the average of the remaining numbers becoming 12.52. And the point is, knowing this, so how do we get it? What number did the teacher erase? Actually, there are 2 ways of solving this problem. So I will tell you, maybe I run through both the two methods. So the method 1 is the regular way. So it's a little bit complicated, but it can ensure you to solve every problem. The method 2 is a little bit, I don't know, abnormal, but it's quite easier in calculating, right? So I just tell you the method 1, the regular way. So we know that we remove, right? So we removed one number between 1 to n, but we don't know which number we removed, right? And then we get the final average. But here is something important. So this remaining average should be within a range. So which range? So let me see. So the maximum average of the remaining. How to make the average of the remaining number the maximum. We can just remove. If we remove the smallest number, this is 1. So if we remove the smallest 1, then the average of the remaining number should be the maximum, right? In this case, the remaining value, so we know that, so the average of a arithmetic sequence is just the average of the first and last term. So this is the maximal average possible. Also, what's the minimal maximum possible? Of course, if we erase the largest number, this n, then the remaining average must be the minimum. And in this case, so it's the average of 1 to n minus 1, which makes it to n over 2. Correct? Correct? Right? Then, yeah, you see, then from here, we will know that as we get the maximum and the minimum of the average, the actual average must be between the maximum and the minimum. In this case, we will get this. So the minimum must be no greater than the actual one, and the maximum, it should be no smaller than the actual one. And then we can get the range of this n. So we times the 2 here, times the 2 here. So this is what? So this is 25.04, right? So this 25.04, no, 23 and 25 plus 0.04. So now we get the range of this n, right? So then we get the range of this n. And n is an integer, so n is either 24 or 25. But it's easy for us to just get the 25 incorrect because it's too close to this 25.04. And so it's too close to extra it's too close to the extreme situation, which means it's very it's very likely to be impossible. On the other hand, 24, seems more reasonable. But anyway, so we can try both of them. How to try? So if we know this n, right? So if we know this n, so if n equal to 24, then let's see. So 1 to 24 is what? So maybe we don't need to calculate 1 to 24 because we can start with this average. So you know that this average is not this is not an actual value because this is rounded to the 2 decimal places, right? So this is rounded to the which means the original value should have a range. So the original value of this average should be, right? So it's smaller than 525 and greater than 515, right? So actually, right? So actually, the average have a certain range of this because this is not an actual value. So this is not an actual value. So now you will see that. So the average is here, and if we know the n, we know the number of terms. Then there are totally 24 numbers. And if we remove one number, so there is only 23 remaining. Then we would have, so this average should be the sum of remaining number over 23. And this fits the need, which is beyond this range. Then let's calculate, right? Then let's calculate. So here we will see this is 12.5.5 times 23. So this is 287.845. Now this is C 288.075. And S is an integer, which means S can only be 288. Then S is 288, S the remaining 23 number sum. So the number removed can be calculated as we just use the 1 to 24, which is what? So which is just n 300 minus this 288. So this is a 12. Okay. As for 25, if you use the same method to check, you will find there's no integer solution for this S. Because if you change this into a 24, if you change this into 24, you will find that S would be inside a narrow range that there's no integer feed need. That's the reason so why n cannot be 25. Okay, because time is limited, I don't run through it here. Okay, this is the method 1, right? So this is the method 1. But we just use, right? We just find the maximum and minimal possible average. And the actual average must between these two situations. And then we solve the problem. The method 1 is here. And then the method 2 is very quick, but is a little bit weird. And the logic is correct, but not that good. So now for 1, 2, 3 to n, right? So what's the average of all numbers? So it must be n plus 1 over 2, right? So this is the average of all remaining numbers, all the original numbers. So then if we remove one number, what would change? What would change? So actually, this is a logic. So I use very often to solve this type of questions because especially for the RMO. So RMO like to ask about this question, and for RMO this average problem, so I will use this way. So you know, so there are see n numbers, and all numbers are consecutive, means they are close to each other, which means if we remove one number from them, what's the change of the average? It will just do a very slight change to the average, right? So because we just, each number, they are very close, and we just removed one from it. So we remove one number from an arithmetic sequence, so the average changed only a little. Which means we can just write it so it's like the original average and the actual average, the remaining average, they are similar. We can treat it as the same. And then we can get n plus 1 around this. So n is around 2404. And then we can easily judge that n equal to 24. Then if n equal to 4, the same with 1. Right. So this is not. So because in mathematics, this is not that correct. But for this type of RMO question, so the average of arithmetic sequence is, so I believe there are 5 questions in recent years asking about this. So this is a very important question type. And to solve this type of question, so we remove one number from a arithmetic sequence. So you can use the method 2, because we just remove one number, the average changed just a slightly little bit. So we can regard that the original average and the final average, they are the same. They are the same. And then we can solve the problem easily. We can just do the estimating and get the number of term or the original m. Okay, yeah. So sorry that this is my third day or fourth day of COVID positive. So my body is not that good. So today I just rush into all the questions. So I am afraid I cannot finish it. But luckily, we finished all the questions. So yeah, maybe you try to. So now next week, the same time, we'll run through the question 11 to 20, which is all about the number theory, or all about the number theory. So I believe so you do this question first, and then next week we will be more efficient. Okay, thank you for that. Bye-bye. Okay. OK，关播了。